dust and spacecraft charging effects near asteroids and comets. And there he is. Thanks, Mihaly.
Thank you. Well, maybe just to save time, I can start the presentation anyhow. The first slide is a beautiful image from Rosetta. And somewhere in the top left of that image is the moon, because some of my talk today is to tell you how much we could learn actually about dust and plasma interactions at other places, not only the ones that are of immediate interest for human exploration, but the ongoing Rosetta mission, which is perhaps the record holder for the number of instruments making simultaneous measurements of all kinds, and the difficulty in analyzing the data. It seemed like a good idea to give them my computer. Oh, there are. There we go. Oh, all right.
I see charging.
There we go. So anyway, let's move on. My colleagues, Shu Wang is responsible for the laboratory experiments that I'm going to report to you, because I'd like to emphasize how important lab experiments are to untangle all the observations that we possibly make. Ove is another theory guy, and Jan is the one responsible for all the computer simulations. There are markings throughout the solar system when we believe that, interactions between dust and plasmas make a major role. And you might argue that these things are of minuscule importance for human exploration, but I have to remind you of the guy who transferred every fraction of a penny in every transaction in a London bank and make billions of dollars, maybe just millions. So these little snippets of features have a possibly much bigger importance to guide our understanding what exactly is going on a surface, in this case the moon. I have to remind you that we carry other things of this kind that I cannot possibly give you a full explanation. These would be the spokes in the rings of Saturn. Even after Cassini is going to complete its mission, that issue still remains open. And of course, we also have these regions where dust apparently accumulates into beautiful Zen garden, even with some raking at the bottom. So, yesterday we had a bit of discussions about swirls and possibly the effect of solar wind standoff at the magnetic anomalies, generating the optical, albedo markings of the swirls. This is a hybrid simulation, which is one level of approximation. You should know the scale, and that's more or less markings where solar wind has access, and it's more or less reproduces where darkness and bright regions emerge on the surface. You could look at better simulations, and this, not better, but different one on a different scale, where more physics is revealed, but on smaller scales. These are peak simulations where both electrons and ions are followed self-consistently. And you can argue that, yes, this shielding seems to work. But notice that the arguments at this point are still at the look-alike. It looks like. And I think we could do much better than that, just beyond the comparing images and comparing the end result of these simulations. And that's the challenge that, you cannot possibly exactly reproduce the conditions that exist on the moon or in spokes, but you could do similar bits in physics in a lab. And that's the challenge then to our colleagues who do the theory or the computations. Do the simulations for the lab. See if you could reproduce what we can give you full data and knobs to turn. And then we could all look back to the moon and see how much trust we could build up in those simulations to understand what's going on the lunar surface. That's a simple experiment with a thermal plasma. That's the experiment where these slides are coming from. It's a flowing plasma. It's a flowing plasma at much smaller speeds than the solar wind. In a year, I promise, somebody from our group will come and show you what happens when solar wind speed ions are hitting a magnetic anomaly. And this is the data. We can measure whether there is access or no access to the surface. We can actually tell you the electric field depending on the orientation of the dipole. So here is the challenge for the computer simulation fellows or colleagues: reproduce what we can measure in the lab. The lab actually is another incredible opportunity to learn about things that we cannot possibly have data just yet, until we can probably return to the lunar surface and design appropriate experiments. Electrostatic forces on the face of these arguments, and I have made that argument many times in this forum myself, is not capable of lifting dust particles. If you are shining a UV light or exposed plasma, you could calculate what we call the plasma space. You can estimate the electric field. You can estimate how much charges you could accumulate on the surface. You take the product of the charge and the electric field, and you fall short even on the moon. You cannot lift particles. That sounds well, and then we go back to the lab. We shine plasma or UV in a crater, and the dust does not listen. It does jump up. It somehow missed Gauss's law in school. I don't know what's happening. Until we realize that actually this problem is not a simple surface problem. You don't really care about the surface charges that you accumulate on the top layer. This is really a characteristic of regolith charging. The photons that come in, of course, in this case, the photons that would hit the surface, they would be recirculated, and you have a balance of outgoing and incoming electrons at all times. The flight time of an electron is nanoseconds. Imagine that photons shine into a cavity where the produced secondaries do not escape, and you can accumulate the charges for long periods of time. And here it is. This is in the plasma. We initially I'll show you the movie in a second. Initially, outside the crater, there was no dust at all. And actually, we can make movies of hopping dust. And then UV alone is not as efficient, but it does do the job on its own. Let's see if I can make this happen. There it is. This movie is done by taking, differences between subsequent images. And by the way, these are not tiny particles. These are tens of microns, easily seen with your naked eye. Here is the size distribution. That's the sieve. There is a standard American series of sieves, 39 to 45 micron that we sieved. You are not surprised that there is a bunch of smaller particles outside the crater after the experiment, because it's very hard to sieve particles below a certain size because they hang on to their bigger brothers. And that force can be actually quite large. What is surprising or stunning to me, that there are huge particles, blobs of fluffy stuff flying out of this crater. They could break off at the edges, they could break off and get rid of their neighbors, but they clank together and land, even 100 micron particles land in 1G. We get it out of the crater. In the moon, that's quite a jump. You could remove particles and rearrange surfaces. In fact, here is a series, and I wish we could run these experiments longer. We'll come back in a year, we'll tell you what happens in the long term. But at least notice the tendency. There is a Zen garden being built just by being exposed to UV or plasma. The surfaces are getting smoother and smoother. It's easier to jump off from the top of a hill somewhat, because the cohesion and the distribution of forces that connect you to your neighbors are somewhat reduced. But at the end, maybe this is the way to make ponds. And of course, this is Rosetta, and I'm not arguing that we should ever consider sending a mission to Rosetta, but I'm here to report to you that there's a lot we can learn there, how to do the measurements, how to figure out these things. Imagine that you are near an outgassing object, and I apologize, typically we don't like equations, but this is the standard way to set up. Neutrals are produced by ionization and lost by recombination, and that's just the continuum equations with the appropriate boundary conditions. And you could actually look at, okay, in steady state, no recombination, I can show you the solution. The neutral density will drop, the plasma density will build up and eventually drop as well. Of course, the total of the two maintains the 1/r² dependence from the point source. You could do this by now. This is much easier than when I started. There is Mathematica. You could code this in and you could solve the partial differential equation. You could even make it up, make a story. This is how I believe the production rate of this object is changing in time. And this is what then the plasma is responding Very near, of course, near to the source, it takes a bit of time to ionize, but then eventually somewhere there is a maximum plasma density as the stuff is flowing away from the central object. Then you could put this into the standard equations. These have been tested many times in the lab. These are Longwood probe equations. What sort of currents are you accommodating? This is what we call an IV curve. This would be the potential on the probe or a dust particle. This would be the current. This is a micron-sized particle at 1.3 AU out in the solar wind. You are generating dominant current. These photoelectrons being released. Of course, if you set the potential to be positive, all the photoelectrons are returning, not escaping. There are secondary electrons, there are electrons in the solar wind, the proton current is negligible. Or you could actually follow the charge as a function of time, and it takes about a minute or two for a micron-sized particle at 1A or at this distance to get into charge equilibrium. If you go near this outgassing object, sorry. Let's go back. Hey. I'm sorry. Solar wind. Near a comet, the story is somewhat different. The densities, the plasma densities are much higher. It is really dominated by the collection of electrons. And as a function of time, this micron-sized particle gets into charge equilibrium very quickly. If you are a spacecraft, of course, you are in charge equilibrium almost instantly. So imagine then, as a function of the production rate, as a function of time, if you are near a weakly outgassing object, as a function of time, regardless how far you are from this object, you will always charge positively. If you are near an object that is outgassing very strongly, almost regardless where you are, somewhere between 50 and 300, the color code is close and far, between 50 and 300 kilometers from this object. If it's strongly outgassing, everywhere you'll be negatively charged. And of course, the most exciting part, if you are at the right place at the right time, to have, depending on where you are near this object, you could go either way, both positively or negatively charged. So this is what we believe the production rate of Rosetta. Very far, it looks like, dud. It's like the moon. As it comes in, it turns into a real comet. As it goes out, it's going to be fade away again. I can take this production and make a prediction. This is what I think Rosetta will be charged to, as a function of distance from the comet, as a function of the comet's distance from the sun. Here is the magic line for the standard production rate, where the potential is actually 0. Above this line, you are positively charged. Above this line, you are negatively charged. But the comet is not steady in its production. There are outbursts. It could be that for a while, the production rate goes a factor of down or factor of 2 down or up. So there is kind of a slope where this charge switch over happens as a function of these two distances. Now the curious thing, of course, the spacecraft is becoming charged. It builds up its own plasma environment, just like the moon, just like any other object in space. So if you put something in a plasma where electron and ion collection is the dominant processes, you'll be maybe not surprised because you took Plasma 101. There is a sheath going to be developing. Both the ion and the electron density is dropping towards the spacecraft, and that is because that's an absorbing surface. But so it happens that the electron density drops faster. So there is going to be an electric field. This is the potential. There is a region which we call a sheath, which is non-neutral region. The number density of electrons and ions does not match. There is an electric field. And there is this curious region, what we call the pre-sheath, where the ions somehow magically accelerate to the right speed, what we call the Bohm criteria. Of course, a sheath could be incredibly complicated if the surface is also emitting. For example, if you are dominated by electron or photoelectron emission from the sheath, that will have a very different profile than just putting in a plasma, and this is the electric field. And anything else in between. You could build up a sheath that is non-monotonic, and there are strong electric fields and double layers near the spacecraft. So one has to be very mindful what a small particle approaching a spacecraft will sense. Am I going to get into your detector? Am I going to never make it? Am I going to be accelerated? So this is the history of various examples. This is all particles are at 3.5 AU. That's a micron, a tenth of a micron, and a hundredth of a micron particle as a function of where Rosetta is with respect to the nucleus. And that's the history. A micron-sized particle more or less achieves a charge equilibrium. A tiny one, the charging time is so long that it goes from the nucleus to the spacecraft, never being in charge equilibrium. It just takes too long. It goes across much faster. Now imagine that this is a positively charged spacecraft and the positively charged particle arrives. Notice this is the history as a function of distance and spacecraft potential. I'm sorry, the spacecraft potential is what I calculate would be the equilibrium here, and the potential history of a particle as it breaks through the sheath. So the particle initially slows down because it feels a repulsive electric field. But then it goes into the sheath, there is an overabundance of the different charge carriers, and then it changes its charge and would speed up. That's curious. If you were to take a different history, like this guy here, a tenth of a micron particle, it turns out it will never make it to the spacecraft. Its charging time is too low, the force is repulsive, and you will not get into your detectors. So, actually, I am at my last slide. I should also get kudos. Surface properties of airless regolith covered bodies clearly show throughout the solar system, at least that the places where we look, be there the ponds, be there the horizon glow at the moon, be there the swirls, everywhere we look, there are fingerprints to tell us that there are processes that is not just gravity and cohesion, there are some other curious things going on between how electrons, ions, the plasma environment, electric and magnetic fields, and dust lives together. If you were to make a measurement, you have to be very mindful that the spacecraft itself is upsetting the environment. Of course, we had these arguments many times. Electric fields on the moon, how would you make that measurement? And before we decide, and I am fully on board, we should have in situ measurements, we have to think long and hard. What is the question you're asking and how do you make that measurement? If, for example, you will make a simple Langmuir probe deployed on the lunar surface, you will measure the spacecraft sheath. There is no reason to go to the moon. I can do that in the lab. Anyway, there are difficulties to make the measurements right. We have to think before we, plunder an opportunity. We have to think very hard. Oops, I'm sorry. That's a good place to finish. In any case, I do believe the laboratory experiments still have room and offerings that we have to, confront, because that's help us to ask the right questions and come up with the right measurements. Hopefully, we'll eventually make right in a swirl. Thank you.
I'll use this one. Either one was hot. Okay. Mihaly, fantastic talk, because both subjects I'm very interested in, both the electrostatic lofting in the lunar exosphere and the Rosetta, because I've just been to the conference in London, and reading the articles and talking with Martin, and what they're finding in COSIMA in the imaging and micro-SIMS instrument is that they're seeing hierarchical clusters that are about 1 millimeter in size, and keep asking, what is the selection effect? So have you calculated anything much bigger? Is there a certain speed where the momentum takes you through the electric charging? Because you've gone up to like a micron in size, and what they're finding is really 15 micron sized subunits up to 1 millimeter in size.
So I'm aware of these arguments, sometimes heated, sometimes collegial.
Yes.
A lot of things have been discussed, like the delivery of 100 micron sized particles coming up near the spacecraft, no smaller, no bigger, that somehow the suggestion that they break up in the electric field in the sheath. We can make these estimates. It seems unlikely to me, but on the other hand, I cannot offer an explanation. There are a curious combination of things, like large particles, indeed, if they are gas-driven from the nucleus, will go slow. Tiny particles arrive fast. So there is a curious sweet spot, that your charging time, your travel time, your crossing the sheath characteristics, eventually we'll sort it out. But I don't have an answer other than I sense or I feel that it might has to do with the type of physics we are discussing here.
Okay, so I'm very interested in the going larger than a micron regime in your calculations to see.
So the large particles, of course, naively would be in charge equilibrium instantly, so that calculation is easy. But then we have to turn this other knob, but our colleagues argue that these are, dandelion bulbs. They're large and incredibly light. So the porosity or the density of these things is aerogel or less. I don't know how to deal with that. Maybe I could talk to you. What's your impression?
My impression is that the particle densities are not 95% porous, that they're more like 70% porous. So there are some approximations. Thank you for that, because it's such a mystery. Why aren't they seeing the small particles that we know are there in some other comet? So is the comet really different, or is the sampling different? Thank you.
I get this? Okay, I'll just sit here and talk then. Wonderful talk, Mihaly. I learned a lot from your discussion here. And I have two comments. One is concerning your experiments and the particle movement. Those are beautiful. In a separate but exactly the same result, I was thinking of as I try to prepare lunar samples into a dish in preparation for measurement. They don't want to stay in the dish. and you learn that turn off the fluorescent lights, make sure you don't have fluorescent lights on because they're going to hop around even more then. It's exactly what you saw in your experiments.
So, of course, we learned early. Where is Eddie here? Anyway, we have previous. So when you sieve, you better do it it's incredible.
Yeah.
It's a health hazard. So we are very worried about sieving anything. So we bought the machines to do the shaking. That's probably tribocharging.
Well, now I have a question too, because your discussion. Please comment on your own dust measurements from the LADI spacecraft, where you did see these particles. Clearly, you must have gone through calculations, et cetera, but.
I was expecting. Where is Jamie when I need him? Anyway, so this is, even if I were to translate the 9.8 to 1.6, the G value at the surface, yeah. I can lift these particles maybe 10, 20 centimeters, maybe even 30 above the lunar surface. They will not go high altitude. So at this point, yes, it is possibly something we have to ponder about. I think we have no say or no understanding or measurement below a kilometer or so. We only could detect the stuff, at orbital heights, 50, 100 kilometers above the lunar surface. To the best of my understanding, the correct interpretation for measurement, we could put an upper limit, which is much below what the visual or Apollo statements were. Yeah. But in reasonable agreement with LAMP and other UV statements, I think there is a whole bunch of richness closer to the surface that LADI did not address. And now I would love to come back to you and says, we have experiments. We could build a set of dusty plasma questions that can be answered if we build the right machine. And it's not the standard electric and dust probes. We have to be a bit more careful. What is that you are asking, and how can the answer be delivered if we had a chance to make this measurement on the surface?
Yeah.
We're going to have to move along, unfortunately. And I encourage you to take this conversation up with Mihaly later on. Thank you again, Mihaly.